My name is George Marcus, and I am an associate professor of physics in the Department of Physics and Astronomy here at SUNY Geneseo. My background is in studying optics and its application in various physical problems. I've done work studying physics of biological tissues in surgery applications. I've studied atmospheric physics. I've studied contamination in both the atmosphere and in liquids. The research that I do here at Geneseo is based on bringing my optical techniques to bear in studying atmospheric processes. We're really interested in the kinds of problems that are associated with the large global climate studies that are a big part of what we're doing right now in science. We try to build in the lab tabletop systems to try and study the atmosphere as a whole. Right? The atmosphere is huge. We don't have a huge lab, so we need to be able to make the atmosphere in our small tabletop setting. And that's the biggest part of the research that I do. And that project has lots and lots of components. We can use lots of different sources. We can use lasers and LEDs and diodes and white light lamps. We can use lots of different detectors, photodiodes, PMTs, all of the technology that is part of the modern era of optics. And we can try to couple those together into these systems. And when students are involved in this research, they can get involved in any of the layers of this. There's the hardware, lots and lots of different pieces. Building a laser diode system, tuning the wavelength of that system, building the temperature and power control of a diode system, building the optical cavities, the actual systems that allow us to create the equivalent of a 1 kilometer long piece of atmosphere in 1 meter on a tabletop. There's a lot of computation involved in this because if this was easy, everybody would have done it already. And so trying to figure out what it means when we see some absorption in our tabletop setting requires some computer control of our data acquisition system and some fairly involved simulations and calculations. And so student involvement runs the range from building the hardware, testing the hardware, machining the systems, writing the software to run the system, and doing extensive simulation and computation, code that can take days to calculate once they're running. I've been building this lab for 10 years, and I don't think it's a lab that will ever be done being built. We're improving every part of it every year in order to try and do better measurements and have measurements that we can feed into the global climate calculation community for them to make better calculations. We provide data and input to those larger scale calculation systems.